Good morning, ladies and gentlemen. We are on to what is entitled Day 5 of Types of Solutions. And Types of Solutions often introduce us to the second unit that we do in the year, but I've included it in the first unit. The first unit is solving multi-step equations, and it's important to know what types of solutions you can possibly get. So up until this point, I've protected you, and I've given you pretty much easy equations where you've had integer solutions, and the integers are the whole numbers and their opposites. So we have seen no partial values. We have seen no decimals or fractional quantities that cannot be simplified to an integer, a whole number, or their opposite. Please recall that the whole numbers start at 0 and go on to infinity. And again, don't include any partial values because they are whole numbers. And the integers are the whole numbers and their opposites. In a minute, we'll go back to having to have a strong definition of rational, which we often remember as fractional. It's any number that can be written as a fraction. That obviously includes all the integers because you could simply put them over 1. But it also includes terminating decimals that can be written as fraction as well as repeating decimals. So rational means terminating and repeating decimal quantities because they can be written as fractions. The opposite of rational would be irrational. Those are numbers that go on forever and do not repeat. There is no way to write them as a fraction, such as pi. That's one of the most popular ones. And any non-perfect square. When you take the square root of a number that's not the result of some other rational quantity times itself, you will not be able to take the square root without it being a non-terminating, non-repeating decimal. They make up the real number system when you take the rationals and the irrationals and you slam them together. All non-terminating, non-repeating decimals, as well as terminating and repeating decimals. That is the number system we work with for the majority of the year. At the end of the year, we'll get a chance to talk about some imaginary complex numbers, which are typically the result of trying to take the square root of a negative, which if you try that on your calculator, you run into some issues with. Okay, now that we've done that little review, it would be a good idea for you to take a moment and make sure that you're on the correct page in your workbook. It's Types of Solutions Day number 5. If you don't have it, you're going to have to copy down all this work and produce it on loose leaf. I am going to need your work by the end of the week. It's going to be handed in one folder. Today I want to talk about the zero product property and being able to solve equations. And before I do that, I would like you to take a moment to pause the video and evaluate these expressions. In Roman numeral 1, we're asked which of the expressions below evaluated can be classified as a positive integer. For all examples, assume all variables represent integers. So what's important for us to do at this point is to simplify these expressions, to type them into our calculator and see what they're equivalent to. And at some point, we want to identify the positive integers. So the positive integers technically would go include 1, 2, 3, 4, and 5. We typically say 0 is neither positive or negative, and obviously we don't want to include the negatives because we were told just to have the positive integers. So we're looking to see which of these expressions evaluate to be a positive integer. Take a minute, pause the video, and see what you get. Assuming that you pause the video, now would be the time where you come back and you check out your work. Letter A, ladies and gentlemen, negative 5 squared, and negative times the negative is a positive. That comes out to positive 25. Any quantity squared is that amount times itself. B is a little bit tricky because when you type it into your calculator, it's going to assume that you want the opposite of 5 squared. So it's going to follow order of operations here, and it's going to multiply 5 times 5, and it's going to get 25, and then it's going to evaluate the exponent and know that that's 5 times 5, which is a product of 25, and then it's going to take the opposite of it. That's why that's coming out to negative 25. And there are some instances where that might come up a little bit differently, but for now, I'm not going to include that as a positive integer. The square root of 10 is not the result of a rational quantity times itself. There is no number times itself that equals 10. Therefore, when we take the square root of 10, we get an irrational result because it is a non-perfect square. 3 and 162, and the ellipsis means goes on forever and doesn't repeat, is irrational, non-terminating, non-repeating. Therefore, it is not a positive integer. Letter D, when you take the opposite of the square root of 25, this gets a little weird later on in the year, but for now, you can assume that that is negative 5, and that would not be a positive integer. Later on, it might depend. You can't take the square root of a negative, because square root asks the question what amount times itself equals the amount underneath the square root symbol, or what we call the radicand later on in the year. And in order to get a negative product in our mathematical system, the real number system, you have to have a positive times a negative, and that number wouldn't be itself. So there is no real solution. There will be an imaginary solution later on in the year. For letter F, 5/10 simplifies to 1/2. You could have simplified that in your calculator, and that would not be a positive integer. It's a rational number, rational meaning fractional, but it is a non-integer. Letter G, negative divided by negative is a positive. Letter H, when you try and simplify this expression in your calculator is going to say division by 0, and it's going to show an error because that's asking how much of nothing can we fit inside a quantity, and that is indescribably large, it's beyond infinite. Therefore, it is undefined, and that would not be considered a positive integer. 5 divides into 0 exactly 0 times, but 0 is considered neither positive or negative, kind of like it's neutral, so we can't consider that a positive integer. Any amount divided by 1 is itself. Any amount divided into itself will divide imperfectly one time. Those are both positive integers. Letter L, any amount divided by 1 is itself, and that's going to depend on what x and y are. So we're not really sure if L would be a positive integer or not. It's fair to put a question mark there. M, however, I don't care what those variables are. It doesn't really matter. Any amount will divide into itself perfectly one time. That's incredibly important in this course, and 1 is certainly a positive integer. Letter N, any amount times reciprocal is really the same thing as that fraction, 5/1, divided by itself, 5/1. Division is the same as multiplying by the reciprocal, and any amount divided by itself equals 1, and any amount times its reciprocal, since that's the same as division, will equal 1 as well, and 1 is a positive integer, so n should be a positive integer. And if you take that and you apply it to letter O, it doesn't really matter what x and y are. We're dividing the same, or we're multiplying the same amount times its reciprocal, and any amount times the reciprocal always equal 1, and that would be a positive integer. Letter P, it doesn't really matter what x and y are. We use this all the time in algebra. When you subtract an amount from itself, the difference will always be 0, and 0 is neither positive or negative, so we can't include that as a rational, a positive integer. So your positive integers up above would have been negative 5 squared, negative 10 divided by negative 5, 5 divided by 1, 5 divided by 5, 5 over 1 times its reciprocal 1/5, 5xy times its reciprocal 1 over 5xy, possibly negative 5 squared, possibly the negative square root of 25, and possibly 5xy. Those will be a little, we can investigate those a little further later on in the year. Down below, I should have had you do this, I guess, as an additional do now problem to see how you did on last night's work, where you could have solved each equation for x, resulting in an algebraic solution. So these are the style of questions we did yesterday, where we talked about not only can you get non-integer solutions when you solve algebraic equations, but you can also get algebraic solutions. And that shouldn't freak you out, because we're always doing pretty much the same thing. In number 1, if we were solving for x, most often when we equation solve, it leads to the least amount of confusion if we begin by distributing. If there is some grouped quantity being multiplied by coefficient, so in this case we're tripling g minus x and another g minus x and another g minus x, that's a total of 3 g's minus 3 x's, but it's a lot of work to do that, so we usually just share the multiplication into the grouped quantity, and we say make sure that you triple g and make sure that you triple x, and that would equal h. And if we're solving for x, we understand that we have to remove the 3 g's. And in order to get rid of the positive 3 g's, we would subtract them. Subtract 3 g's, or as I like to say, add the opposite to both expressions. And we're left with negative 3x equals h minus 3g is just h minus 3g. It's exactly what it sounds like. We don't want negative 3 x's, we want just 1. So we're going to divide out the coefficient of negative 3 in both expressions. And we're going to be left with x equals h less 3g divided by negative 3. There are other ways to interpret this at this point. You guys know that division is the same as multiplying by the reciprocal. So you could say, Tooch, isn't h really negative 1/3 h minus 3g? So we could divide out the negative 3 in the denominator and write it as a negative fraction. And with a negative fraction, it doesn't really matter if the negative is in the numerator, if the negative is in between at the fraction bar, or if the negative is in the denominator. We consider it in simplest form with the negative in the numerator, but they all interpret. If you type all 3 of these expressions in your calculator, all 3 of them are going to say the same thing. They're going to say negative 0.03 repeat. Oh, sorry. They're going to say negative 0.3 repeating, negative 3/10 repeating. So they're all going to have the same decimal value because there's one negative sign indicating that we're going to take the opposite value of that quotient. So you could have said, Tooch, isn't division the same thing as multiplying by the reciprocal? Can I multiply by negative 1/3? If I multiply by negative 1/3, isn't that really the same thing as dividing by negative 3? Couldn't I write this simply as negative 1h divided by 3, and negative 1/3 times negative 3g, negative times a negative is a positive, wouldn't I get positive 3g divided by 3? That is another mathematically equivalent presentation. That's the result of distributing or sharing the division of negative 3 with each term. H divided by negative 3 is negative 1/3 h, and negative 3g's divided by negative 3. Technically, at this point, you could say 3 divides to itself one time, and you get x equals negative h, you don't need the 1, divided by 3 plus g. They are all correct interpretations. If they all make sense to you, you're a beast. If you get at least the first one we did, you're in good shape. If you're able to think through the other ones, at least one more, you're in excellent shape. So know that this is the type of stuff that I'm going to build your understanding of all year long. So if you don't get it all immediately, that's okay. You could try number 2 on your own if you want to pause that for a couple seconds. And you'd have to put up a fence. And you're solving for x. Give it a shot. See if you can think of a way to start. Assuming you'd paused it and at least tried to think about it a little bit, there's a couple of ways to interpret this question. I'm shocked at the way I'm showing it here because I would have distributed first. I don't know why I chose to clear the denominator of t right away. I think that it would have been more productive if you're ever able to clear parentheses to do that first. I didn't even know that was coming. I'm like a little disappointed in myself. I would have preferred to have distributed in the numerator 5 times x and 5 times 2y and say 3 equals 5x plus 10y divided by t. And then my preference would have been to undo the denominator of t, because that's what's going to make this really hard to solve, is the fact that we're dealing with a fraction. Fractions have denominators. Denominators mean divide. Undo the division with multiplication. Multiply the expression on the left by t, or right, excuse me, and multiply the expression on the left by t. You can multiply an equation by whatever you want, as long as you do it equally on both sides. And if you were to do that in the expression on the right, you would get, sorry, left, excuse me, t times 3 can be rewritten as 3t. It's a little awkward to call it t3. We're just using the commutative property of multiplication to rearrange the multiplication or to reorder it, and it just makes more sense that way, and it's easier to interpret. And in the expression on the right, t divides to itself perfectly one time, and we're left with 5x plus 10y divided by 1, but anything divided by 1 is itself, so we leave it there. If I then pick it up where we left off a moment ago, or if I pick it up from there in the answer key, you can see that the next step would have been to subtract 10y's from both expressions. We want to get the 5x's alone. So we're going to move or remove the 10y's with the additive property of equality. I know it's subtracting, but subtraction is the same as adding the opposite. And you can add whatever you want to an equation as long as it's equally on both sides. Once you've done that, positive 10y and negative 10y cancel, and we're left with 5x's equal to the expression on the left-hand side. We don't want 5x's, we want just 1. So we're going to undo multiplication with division. Divide both expressions by 5. 5 will divide into itself perfectly in the expression on the right. And we're left with x equals 3t minus 10y divided by 5. Now, technically, you could share the division of 5 with each of the terms. You could distribute that division, and you could write 3t over 5 less 10y divided by 5, and you could actually perform the division of 5 into the coefficient of 10. 5 would divide into itself once and into 10 two times, and the entire relationship could be written as x equals 3t divided by 5 less 2y. So there are 3 presentations that are all mathematically equivalent. If you understand at least the first one, you're in great shape. If sharing or distributing the division of 5 into the numerator, into both terms, makes sense to you, you're in very good shape. And if you understand all 3, you're in amazing shape. Cool. I have to get to actually the meat of the lesson at this point. So today's lesson is specifically on the zero product property. And the zero product property is going to have us jump to this section of today's work where I have to do some describing to you. So the first portion of the description is really simple because it's going to go back to two-step equations, which is where our equations solving started. And you started to see these way back in 6th grade. So you've been doing that for quite some time. And a two-step equation is simply where you have the variable multiplied by some coefficient and a numerical constant. Twice the value of x plus 8 equals 20. And you can almost think of what the answer is because you're like, wow, it's really easy. If I just didn't have that plus 8 thing, I could probably think of what number I double would equal the product. So a lot of people are like, well, let's get rid of the 8 then. Let's just take 8 away from both expressions. And then what we would find out is that we really just need to think of a number that if we were to double it would equal 20 less 8 is 12. Well, I know what number you double and get 12. That's got to be 6. So we could either divide out the coefficient of 2, or we could multiply by the reciprocal. Division is the same as multiplying by the reciprocal. And instead of dividing by 2, we can multiply by a half. Half of 2x's is 1x, and half of 12 is 6. The answer is 6. So there's a couple of things that are interesting about this. Thing one, it goes over a lot of the properties that we're going to use in all of our algebraic solution and solvings throughout the year. Most often when we equation solve, our goal is to get them down to a 2-step by simplifying the expressions appropriately and using correct algebraic steps. And there aren't a lot. There's really like 5 to 8 of them in the whole course, and you just got to know them really well. When you get to a 2-step, we usually undo the numerical constant first. That's the number all by itself without the variable. And we usually add the opposite. So we kind of work backwards through PEMDAS. That's how I often describe this. If you think of PEMDAS as the acronym that describes how we would evaluate expressions, we follow that if we have numbers within a mathematical sentence and we want to know what those numbers and operations come out to. But if we have variables involved, we usually want to pull the equation apart and we go backwards. So we undo the addition and subtraction first using the additive property of equality. Once we've undone the addition and subtraction, the next step is typically to undo the multiplication or division. And we usually use the multiplicative property of equality. If we have to undo multiplication, we choose to multiply by the reciprocal. That's the same thing as dividing, or we just divide. And that undoes the coefficient, the amount being multiplied by the variable. So that's really what a 2-step consists of. But what I want to introduce you to is something that very few classes talk about, and that to me is absolutely amazing. You can solve a 2-step equation using what's called the zero product property. Now, the zero product property is absolutely fascinating because the zero product property is what we use to solve all other types of equations in this course. This particular equation that you've been working with in many different forms and ways for the last month is called a linear equation. And we're going to start to graph them in the next unit. Hey, I bet you can't guess what a linear equation is going to graph into. What sort of picture? Maybe you see it. It's right there in the word linear. It's going to make a line. It's going to make a straight line. Linear equations are what we call first-degree polynomials. They're first-degree polynomials because the exponent on x is always to the power of 1. We don't even bother writing it. So they're first-degree polynomials because they are x to the first powers. And when you graph an x to the first power, it's always going to make a straight line. When you graph all other things like an x squared, weird things are going to happen. X squared is going to make a u. Then when you do x to the third, it's going to make an s. And it's going to get crazier and crazier as we continue to increase the exponent. Or the exponent becomes a fractional value. Weird things are going to happen. So because we're dealing with linear equations, they're really kind of easy to think about, as we said a moment ago. I used to give you guys puzzles in 6th grade, and maybe I'll have time to do it in class, where the variables were replaced with pictures, and it'd be like 2 times hamburger plus 8 equals 20. And you'd be like, oh, hamburger, that's so funny. If we just take away the 8, 2 hamburgers equals 12. And most of y'all could do it in your head. So when we solve linear equations, they're so easy that we typically don't think to set the equation equal to 0 and use this more powerful method of solving equations that we use for almost all other equations throughout mathematics. Linear equations most often simplify into two-step algebraic equations. And because they simplify into two-step algebraic equations and are so easy to consider, we usually solve them by undoing order of operations. It is completely correct to try and solve the two-step equation equal to 0. And some kids freak out when that happens, but you don't have to. If any amounts are being multiplied together to equal 0, then the result would suggest that one of the amounts, if their product is 0, at least one of the factors must equal 0. And that's what I want to consider in just a moment. This is how Texas Instrument, the calculator, solves all of your equations, and this is how most nonlinears are solved. Okay, so if you take a look at the example problem, what sometimes happens to students when they get confused is they're like, I gotta undo, I gotta subtract something. Tucci said subtract something. So they solve the two-step we saw up above, and on accident, sometimes they'll subtract the 20 from both expressions, or they'll add negative 20, which isn't wrong, because you can add whatever you want to an equation so long as you do it equally on both sides. And they end up with 2x less 12 equals 0. Now they could then just add 12 to both expressions and get 2x equals 12, and then divide by 2, and then we get x equals 6 like we saw a moment ago. But they could also use this more advanced method that we use for all other equation solving for the rest of the year with a linear, even though most people don't choose to. You could take the expression on the left, 2x less 12, and you could say, hey, you know what I realized? Both 2x and 12 are divisible by 2. It's almost as if someone doubled x and doubled 6. They shared or distributed a 2 into two terms. And you can undo that distribution. Undoing distribution is technically called factoring. Some people call it reverse distributing. And you can pull the 2 out of the quantity x less 6. So if you pull the multiplication of 2 out, you have to recognize that it should be multiplied by both x and 6, and you'd have to put them in parentheses. You then have an expression that says twice the quantity x less 6 must equal 0. If you have two factors multiplied together to equal 0, one of them had better equal 0. So in this particular instance, 2 can't equal 0 because 2 equals 2. So usually what we do is we set up a little t-chart here. And we say, well, 2 can't equal 0 because 2 is just itself. However, the quantity x minus 6 could equal 0, because if x minus 6 equaled 0, then 2 times 0 would equal 0. So if the whole grouped quantity were equivalent to 0, then twice 0 would be 0, and the equation would be true. Well, what minus 6 equals 0? That's kind of an easy question. It's got to be 6. But if you want to solve that little equation, add 6 to both sides, and you get the same answer. Folks, this is a really powerful introduction to a really powerful technique because it's not that hard right now. So I'm going to show you what I mean. Flip the page. As you go to the back, ladies and gentlemen, I'm asking you to solve the linear equation with the methods we've talked about all year long in part A. And then in part B, I want you to try and solve it set equal to 0 by using the zero product property. So product means the result of multiplication, and property means a rule. Zero product property means you can set an equation where you have amounts multiplied together equal to 0, and that will help you to solve the actual equation. And after you have set it equal to 0, I want you to try and reverse distribute, which is called factoring later on in the year. And you'll factor out the lead coefficient, the one on the x variable, from the entire expression. You'll undo the distribution, and then we'll solve it appropriately. So in 1A, ladies and gentlemen, if you're solving this equation traditionally, you'd put up a fence. You'd say, man, it'd be really easy to consider what number I'd have to triple to equal an amount if I could just get rid of the minus 4. So to get rid of the minus 4, let me add 4 to both expressions. And I get 3x equals, if you have to do that on your calculator, go right ahead, negative 19, and you add 4 to it, you move 4 units to the right closer to 0, and the result is you're at negative 15. We don't want 3 times the value of x, we want just 1x. So we're going to divide out the coefficient of 3, and we end up with x equals negative 5. And we can check our work. Is it true that 3 times negative 5 less 4 equals negative 19? You could just type the expression into your calculator and hit enter. And if you were to do that correctly, you are going to get negative 19 equals negative 19. The expression on the left is equivalent to the expression on the right. That's the answer. Now, what I want to show you is that if you were to have made a mistake here, so long as you're performing correct algebraic process, you can always get the solution. So there are students who get confused for a bunch of different reasons. And they're like, oh, I know that Tucci said to start with addition. I guess I should get rid of that negative 19 thing. That's bothering me. And you'll have students that'll come in here and they'll be like, I'm going to add 19 to the expression on the right and the expression on the left. And this is where, for in class, I would normally say, folks, can your classmates add 19 to both expressions if they want to? And you think about it and you go, yeah. And I go, yeah, you're right. They can. Of course they can. You can add whatever you want to an equation so long as you do it equally on both sides. Some amounts that you add would lead to more efficient equation solving than others. But this isn't wrong so long as you show it correctly. Positive 19 and negative 19 equals 0, which is fine. You can solve an equation equal to 0. And we're left with 3x. Negative 4 add 19 to it is going to go all the way to positive 15. So now at this point, you could subtract 15 from both sides and then divide by 3. But if you want to practice the advanced method that we use for a lot of the other difficult equations throughout the year, I'm going to suggest that you undo the distribution of what we call the lead coefficient. The lead coefficient is the number attached to the highest exponential term, which in this case is x to the first, highest exponential variable term, which is x to the first. So if you were to divide a 3 out of 3x, you'd get 3. And you'd have left over an x. And we're going to have to put that as part of a grouped quantity that we're distributing into because we're undoing distribution. If you divide 3 out of 15, you get 5. So it should be true that triple the value of x plus 5 would equal 3x plus 15. And you can redistribute in your head to prove that. Or if you really need to, you could write x plus 5 plus x plus 5 plus x plus 5. Oh my God, this would drive me crazy. Please don't do this. 3x plus 15. And now what you're able to do once you get to this step is use what we call the zero product property. You have an amount 3 tripling, or you have 3 tripling the amount x plus 5, and the result is that we equal 0. So if we have two amounts multiplied together, something has to equal 0. And 3 can't equal 0. That won't work because 3 equals 3. But it is true that with 3 is being multiplied, x plus 5 could equal 0. We just have to consider what number plus 5 would make the grouped quantity equal to 0. And that should be like a really silly question. Teach, what number plus 5 would equal 0? Well, wouldn't it be negative 5? Isn't any amount plus its additive inverse equal to 0? So we're able to suggest that if we set up a little t-chart here to separate our work and organize it, that 3 can't equal 0 because 3 equals 3. However, x plus 5 could equal 0. And right now you could just say, Tooch, I know what it is. It's got to be negative 5 because positive 5 and negative 5 equals 0. Or you could subtract 5 from both expressions and solve a one-step equation to determine that x has to equal negative 5. The exact solution you get when you solve a two-step equation traditionally. The only difference is what I just showed you is what we're going to use for the rest of the school year. It's absolutely fascinating, incredibly powerful. Cool. Take a look at number 2a, and if you want to try it on your own, you could pause the video and see what you're able to come up with. If you pause the video, ladies and gentlemen, you might have chosen to subtract 6 from both expressions. When we solve a two-step equation, typically we undo order of operations. And going backwards through PEMDAS, we would choose to undo the addition or subtraction of the numerical constant being added to the variable term. Positive 6 and negative 6 are additive inverses, and when we add them together, or if you subtract it, the sum is going to be 0, and we're left with negative 2x equals 27 minus 6 is 21. And then we would have to divide both expressions by negative 2. Negative 2 will divide into itself perfectly one time, leaving us with just x. And I believe we should get, this looks like negative 10.5, assuming I did it correctly. And I'll have to check that. That would be a non-integer rational solution. We could have left that as negative 21 halves. That would be a better presentation for a lot of the work we're going to do for the rest of the year. We almost don't want it in decimal form, but that's okay for now. So let's see if this works. Is it true that negative 2 times negative 10 halves increased by 6 will in fact equal 27? If a negative times a negative is a positive, and when I double 10.5, I get 11. No, sorry, I get 21. And 21 plus 6 equals 27. And 27 does in fact equal 27. So it appears to work. Cool. Okay, so now I want to see if we could have done that differently. And I want to show you the method that most people don't show now, but I believe they should. Because if we get you good at understanding how this works now, when we get to the more complicated stuff later on, it's going to make it super easy for you. Tooch, I got lost. I wanted to solve this equation. For some reason, I subtracted 27 from both sides. Or as I like to say, you added negative 27. Can you subtract 27 from both expressions? Absolutely. Technically, you're adding negative 27, and you could add whatever you want to an equation so long as you do it equally on both sides. So what's going to happen is in the expression on the left, you're going to have negative 2x. 6 minus 27 is going to take you all the way to negative 21. And positive 27 and negative 27 are going to cancel. They're going to equal 0. Since you have an equation set equal to 0 at this point, it would be really awesome if you could somehow represent it as amounts being multiplied together to equal 0. Because if you have amounts being multiplied together that equal 0, one of them is going to have to equal 0, one of those amounts, whatever those numbers are. So in order to do that, what we typically do is we divide out the lead coefficient of negative 2. So we're going to reverse distribute negative 2. We're going to divide it out. And to divide it out, when you divide negative 2x divided by negative 2, you're just going to get 1x. When you divide negative 21 by negative 2, you're going to get positive 10.5. And that's all going to be equal to 0. Now that you have this expression represented as two amounts multiplied together, or two factors, that's what a factor is, equal to 0, something has to equal 0, either the negative 2 or the quantity x plus 10.5. Well, we set up a t-chart here to organize our work, and negative 2 can't equal 0 because negative 2 equals negative 2. However, it is possible that x plus 10.5 could equal 0. And the question then becomes, what would we add to 10.5 for it to equal 0? And the answer should be negative 10.5. It's additive inverse. But what we usually do is we solve a one-step equation. We say subtract 10.5 from both expressions and get x equals negative 10.5. Ladies and gentlemen, this is the lesson on solving two-step equations using the zero product property. It is considered an advanced skill because we use it later on to solve nonlinear equations, and that makes up the entire universe beyond linears. Linears are like the Earth in the universe of equation solvings. It's one small little planet. And then there's everything else. There's literally hundreds of billions of other planets out there. There's hundreds of billions of other equations we have to solve, and that's the method we solve it. And why other people wouldn't teach it to you right now is beyond me, but we do. I appreciate your time. Good luck with the Ed puzzle. That's all you have to get done today. I miss you, and I'll see you tomorrow. Be well.